Alright, in this video we're going to take a look at how to solve several different types of equations by graphing and also algebraically. So if you feel like during this video you want to just try something on your own and see how it goes, you can pause it and then maybe check back after a minute or two and see if you had the correct answer, or if you feel like you need a little more guidance, you can watch and walk through the whole thing. Make sure there are some questions I'd like you to answer as you go through, so make sure you are answering those if you're pausing the video or fast forwarding or rewinding, things like that. Okay, so our first equation here we have, it's a quadratic. We have the quantity x plus 1 squared minus 2 equals 7. So we're going to solve that by graphing. We can do that first. Really what we're going to graph is each side of the equation, this side and this side. So we're really graphing basically like y equals x plus 1 squared minus 2, that's a parabola, and then we're graphing the other side of the equation just as a 7. So if we start with the 7, that's just going to be a line at 7. 1, 2, 3, 4, 5, 6, 7. So go there, I'll make a couple points on there just so I can sketch that out. Okay, so we have a line, horizontal line. And next we'll graph the parabola. So parabola, we have an HK, or vertex in this case, of -1, -2. So we'll plot that first, -1, -2. And if we remember our pattern for parabolas, we're going to go right 1 up 1 from the vertex, right 2 up 4 from the vertex, and we'll maybe go one more, right 3 up 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And that was, we got those numbers basically by squaring 1, squaring a 2, squaring a 3. And that's going to mirror it on the other side. And this one over here. Okay, so we have two lines graphed, or two functions graphed. And what we're looking for really is where the lines are going to intersect each other. So we see there's two right here. So when that x is 2, and when x is 1, 2, 3, -4 is where those meet up at. So we have two solutions looking at the graph. Okay, so solving this algebraically, we can do a few things since it's a quadratic, but one of the ways we can solve this is just isolating the squared and then eventually square rooting everything. So if we add 2 to both sides, we get 9. Now we have the squared all by itself, we can square root it. We'll get x plus 1 equals square root of 9 could be 3, or it could be a -3. So I'm going to, -3. So we're going to write two equations and solve those, and we would get our same two answers. Okay? So you could also solve this another way by actually multiplying this out. If you like FOIL, we get x squared plus 2x plus 1, then we have the -2 and equals 7 still. So if you wanted to multiply this together, you could. And then combine all your like terms and get everything to one side. And we can end up factoring this, and we'll get the same exact values when we factor. So this one you have an option, right? Things that multiply to -8, 4, and 2, we'll make one of them negative to get us a positive 2x when we put it back together. And then you'll get those same answers from graphically and from the other algebra equation. So something we've talked about before, but I just want to make sure we point out again, is what extraneous solutions are. And an extraneous solution technically is a solution of a simplified version of an equation. That does not satisfy the original equation. Another way to think of that is the value we get is excluded from the original domain, so we can't actually use that. So there's a few questions I want you to answer on this page before you go on to the next one. So think about what are the two separate equations we graphed basically to graph this, and then where do we find the solutions to this question on the graph. Okay. Next, let's look at a different type of functions. We have a square root function. So again, we really are graphing this one side and then the other side and seeing where they intersect. So this side's a line, so I'll start with that one first. 1, 2, 3. Slope is -2, down 2 and over 1, down 2, over 1. We'll go a couple of the other direction, up 2, over 1, up 2, over 1, up 2, over 1, up 2. I don't know when this is going to end up graphing or crossing, so we'll just go mostly the whole length there. If you want to use a ruler for this, that would be probably a little bit better. So then our other side, we have a square root function. Remember, that's like a shooting star. And our vertex is, our starting point would be -7, +1. So we'll do that. 1, 2, 3, 4, 5, 6, 7, and up 1. And to get our square root function graphed, we basically rooted a 1. So if we square root of 1, you get a +1. Square root of 4, 3 is a 2. Ooh, that looks good. Square root of 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3. That's probably good. If you can see where our lines are going to intersect, it's only going to be this one time right here. So that would be, let's see what number, 1, 2, 3, -3 for our solution. Okay. Algebraically, we want to also see if we get the same answer. We're going to isolate the square root function. That's really what we're just doing. We can isolate that. We've done this type of equation before. X + 7 equals this. And we'll square both sides. I would highly recommend writing this side twice instead of just squaring each part, because that's not correct. This left side is just x + 7. So if we multiply that right side out, we'll get -2x times -2x is a 4x squared. -2x times -4 is -8x, or sorry, +8x. The inner ones are going to be another +8x, and then the last together will be +16. Just foiling. Let's get everything on one side. We're going to have a quadratic again, and we can factor that. This is 16. If I take away 1, I get 15. And then 16 minus 7 is 9. So we'll factor that. Again, if you feel like you want to pause, or if you want to just try this yourself, you can do that and come back. We can factor with the box and diamond, or just guess and checking. Things that multiply to 9, we could use 3 and 3. And we'll make it all positive. So when we solve those, if we set each equal to 0, we get -3/4, and we get -3. Now we see from the graph, it only intersects at one point, at -3. This one is the extraneous solution. And what's really happening, why we're getting that, is when we when we squared this side, that would have turned into x + 7, whether or not this was a positive square root originally or a negative square root, or both. It would have become a positive x + 7. So remember that positive square root means the top half. The negative square root means we got like some bottom, half that's reflected down here. So that's where that secondary solution is coming from, but really we didn't have both the positive and the negative square root in our original question. So that's why we get that extraneous solution. Okay, looking at one more here, if we get absolute value, how do we graph that? Again, this side versus this side. This side's a line, 1, 2, 3, 4, 5. Our slope is 6, 1, 2, 3, 4, 5, 6. I'm just going to pretend that that fits on there because it's pretty close. And we'll go down 6 maybe. 1, 2, 3, 4, 5, 6, and over 1. 1, 2, 3, 4, 5, 6, over 1. So we've got a line, and we're looking, where does that intersect with our absolute value? That's going to look like a V. So our absolute value graph, we have a vertex of 4, 5, and this time we have a stretch factor. 1, 2, 3, 4, 1, 2, 4, 5. All right, so our stretch factor, normally for absolute value, it's basically over 1, up 1, over 2, up 2 from our starting point, and then reversing that to go the other direction. But now these numbers are going to be doubled. All right, so from our vertex, we're going to go right 1, up 2 this time, right 2, up 4, and we can do one more time, up right 3, up 6, 1, 2, 3, 4, 5. Again, we'll just pretend that that fits up there. It's really close. And we'll mirror that on the other side. 2, up at 1, 2, 3, 4, up 3, and it's going to be that point right there. So we get a V. Definitely make this a sharp V versus a parabola. So we see where that intersects is when x is worth 1. So there's our solution. Okay, algebraically, if we get the same thing, again, we're going to isolate the absolute value symbol, just like we've been isolating all the other functions before. So we're going to do the reverse of PEMDAS. So get rid of that adding first. Then we're going to get rid of the times 2 by dividing by 2. All right, so we're here. Now, we probably haven't seen an absolute value that equals something with an x on it before. If this was just absolute value of x minus 4 equals 3, we'd make two equations, one that says x minus 4 equals 3, and one that says x minus 4 equals negative 3. We're going to do basically the same thing, the positive and negative version of that, positive negative version of that whole entire quantity. So we're going to still do x minus 4 equals 3x, then we'll do x minus 4 equals the negative version of this, which is just negative 3x. If there was two terms right here, let's say it was 3x plus 1, we'd have to do negative of both of those terms. And then we'll solve each of them. So we'll minus x, we get negative 4 equals 2x, divide by 2, x is negative 2. The other one, we get negative 4x equals negative 4, we get x is 1. Okay? So this again, we have an extraneous solution here of that negative 2, that our graphs don't intersect there, and it's not like we were missing it, they're not going to intersect. So our answer is just x is worth 1. So again, one more question on the end is, should our answer contain just the x's, or should it have been an x and like a y point, you know, like 1, let's see, that would be at 11, because that's right off of my graph, if that should be really our solution. Well, really in the original question, it was just, the only variable present was an x, right? So our only solution is going to be x. If we add in a y, there was no y in this problem to begin with, so that wouldn't make any sense. So just the x is our solution for these kinds of questions. Make sure you bring any questions you have to class, or make sure you ask some other time to make sure that gets clarified.